This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and I have with me today Dr. Justin Dimmel, a new PhD who's going to be graduating very shortly from the University of Michigan and headed on his way to the University of Maine in the fall. Justin, thanks for being here.
Thank you, Sam. Wonderful to be here.
We're going to be talking about Justin's article published in the Journal for Research in Mathematics Education, Volume 46, entitled The Semiotic Structure of Geometry Diagrams, How Textbook Diagrams Convey Meaning, which, Justin, you co-authored with Dr. Pat Herbst. But, Justin, as you know, because I know you're a listener to the podcast, I like to start with people's dissertation just to get that on the record before we move into the article. So, what was the topic of your dissertation at U of M?
My dissertation looked at the way proofs in geometry classrooms get communicated by teachers and students. And what I was interested in was, in some ways, working with the approach to geometry diagrams that we'll be talking more about when we get into the article, and wanting to see how do proofs and how do the conversations and the way that diagrams get used in classrooms actually come into teachers and students that are doing proofs in classrooms as opposed to just looking at diagrams in textbooks.
Mm-hmm. And that's with Dr. Herbst?
And that was with Pat Herbst was my dissertation committee chair. He's also my advisor. And in fact, we're at AERA right now,
mm-hmm.
and we do have a session on Saturday. People are, well, maybe some of the listeners have attended that session, but we'll be talking about that work at AERA.
Oh, great. You mentioned it's connected, so you've really been thinking for quite a while now in this space of geometry textbooks, geometry diagrams. So this article digs pretty deeply into geometry diagrams specifically. So I was wondering, what was it that led to this interest that's kind of sustained you for several years on geometry diagrams?
It comes right from my experience as a high school mathematics teacher. My experience teaching math is a little off the beaten path. I was working at an independent private school called the Island School, which was this adventure-based education place where I had a lot of autonomy about the curriculum that we were able to teach. And the math department there, we put together this program of learning geometry and trigonometry through classic problems from nautical science. So things like the longitude problem, like why are the days shorter in the winter, the navigation problems, things that involve visualizing the Earth and space and being able to take the appropriate two-dimensional cross-section of it and represent that as a diagram to solve problems. And I was endlessly fascinated by the range of abilities that my students would show. With some students, it seemed knew almost immediately how the description of a problem or the description of a situation could be translated into a geometric diagram that would let them do work on it, whereas other students were at a complete loss for how to even get started. And that was the first inkling that I had that geometry diagrams as representations, that as a mathematically minded person, I think I, like lots of mathematically minded people, take those representations for granted. It seems completely transparent or clear to me what diagrams are representing when they're supposed to be representing something. But my experience as a teacher helped me understand that this is actually a challenge for people that are approaching geometry or learning geometry for the first time. That was the gestalt of the idea. And then at graduate school, working with Pat's done work with the ways that students interact with diagrams, and that provided an academic resource that I could use to try to understand how students are engaging with diagrams, at least initially.
Mm-hmm. So the article in Jeremy, The Semiotic Structure of Geometry Diagrams, we all kind of probably have an intuitive sense of what you mean by geometry diagrams, but I'm just curious if you could say more about how you conceptualize diagrams kind of intellectually for this study.
For this study, we, and I think you mentioned that Pat was a co-author with me on the paper, we looked at geometry diagrams as visual texts. There's been a lot of exciting work in linguistics and extension of linguistics to multimodal resources, not just text. but things that are beyond text that we still use and take meaning from. There were tools then from social semiotics or systemic functional linguistics that were available to us, and we go into much more detail in the paper, but we look to those existing frameworks to provide inspiration for how we might describe in a particular way the different types of information that geometry diagrams can convey.
And so I was excited to see in the paper how you actually visually use diagrams yourself to lay out a little bit of your analytic framework that you took on the diagram. So using systemic functional linguistics, which is very much about the choices, a lot of times even unconscious choices that people make whenever they're creating a text. They choose to say this instead of that, or they choose to put this modality on instead of that modality. And in terms of diagrams, you laid out these choices or a string of choices. Could you say a little bit more about how you did that?
Part of this came from wanting to look at the kinds of uses students might put diagrams to when they encounter a diagram and they're trying to use it to solve a problem. And we were looking at textbooks as just one way of where you have this, it's almost like you have a zoo of diagrams. You have a kind of supply of diagrams in a textbook, so we could look and see what are the opportunities that the diagram provides for students to do different kinds of mathematical work. But what we noticed is that in some instances you might have, for something like a diagram that accompanies the tangent segments theorem, right? So if I have a circle and if I have two lines tangent to the circle, then if the lines aren't parallel, they intersect at some points, and then the segments are congruent. That's the tangent segments theorem, not stated very succinctly, but that's the idea. And in some cases, you would see some diagrams would have different thicknesses of lines, some diagrams would use different colors, some diagrams would have arrows or other symbolic markings, and yet you have this range of ways of representing what is ultimately the same mathematical idea, the same theorem, right? Like it's the statement of the theorem wouldn't change, but the visual representations that accompany the statements of the theorem in different books might change.
Yeah, and you even go into the labeling too, like labeling with capital letters, lowercase letters, Greek letters. Those are different choices as well.
Right, there's different choices that get made. And as an author of a diagram, if you're creating a diagram, maybe you're not aware of these choices, or maybe you're just doing what you learn to do or what seems natural. But we wanted to look at them as text that students are encountering. And as students, where you're not familiar with the representation, you're trying to learn how these things work, it seemed like it was possible that some of these differences you might get carried away or fixated by, like the use of color or the use of different weights, like what the arrows on the ends of the lines mean. So you're tuning into different aspects of the diagram, but it isn't necessarily clear to you what all of those different parts of the diagrammatic text mean. And looking at them as visual text that span this system of choices, I can make this line dotted or not, I can make this line heavy or not, I can have this part be dashed or not. All of those things are, meaning ends up in the diagram, whether you as the diagram author want that meaning or not. Just like what happens when you write something and you don't really have any control over what it ends up meaning, or when you say things and you lose control in the same way. And that starting point and the systemic network and this way of laying out the trees of choices seemed like I wouldn't say an easy way, but it seemed like a natural way to try to capture this range of variation we were encountering when we were looking through textbooks at, again, purportedly the same problem or the same theorem, just with a different visual representation of it.
I think that's a contribution from the study, is just going through the work of laying out those choices in that framework. And then, of course, you applied the framework in a pretty big way to textbooks across time. And you go back into history quite a ways, so I was wondering what you saw as the value in looking at textbooks over time, rather than, say, doing a study just of current geometry textbooks, as some of us have done in the room. But yeah, what did you see as the value of looking really across time at these diagrams?
Yeah, that's a great question, and I think something we talk a little bit about in the paper is just the way that textbooks can provide there's kind of like this archaeological record, right? We don't know necessarily what was happening in geometry classrooms in 1910 or 1915.
Yeah, we don't have the videos of those anymore.
Right, we don't have the videos, are lost to history, right? But we do have, we have these texts that just endure as a representation of, certainly not the enacted curriculum necessarily, but maybe the intended curriculum. So what what were people maybe expected or trying, like what was the target, what did it look like? And then the other thing that you have, and I guess part of this also follows on some of the work that Pat did early on to talk about different eras of geometry textbooks. Looking back at the older textbooks, it does give you some sense of the kinds of mathematical activity that students may have been expected to do. Mm-hmm. And then wanting to see, one thing that stands out immediately if you look at an old geometry textbook, there's fewer diagrams for one thing, but then there's also the diagrams use a more primitive set of visual symbols, you might say. Nowadays, the idea that there's arrows on the ends of segments that are meant to be lines as opposed to segment, that's something that almost universally happens when you're looking at geometry diagrams in textbooks now. But 100 years ago, it was still the case that a segment could represent a line or a segment, and that was something there wasn't that distinction in the visual cues from the diagram itself that we've now encoded for students. So it does seem like, looking back at these old diagrams, you do get to see different kinds of work that students may have been expected to do, and even different ways of translating or creating diagrams in the case where diagrams weren't present for the problems that students were assigned.
Yeah, and thinking back to your kind of choice tree where you make different choices about things, in the past, the choice might have not even been a live choice yet, because now we have the choice of, like, do I mark parallel lines with this kind of little, arrow on the line, or do I mark with hash marks kind of congruent segments, or do I mark congruent angles? Like, now we have kind of choices for that are pretty active live choices. But in the past, if that was not even part of making a diagram, that wasn't even really a live choice, right? Like, if it hadn't become a thing yet to put those little hash marks, or to put the little angle markings, or to put the little box to mean perpendicular, or whatever it is.
And we can't say for certain when that became a thing, but it does certainly seem like there's strong evidence that was a 20th century innovation, and that it was something that came from geometry teachers as opposed to... And not that the people that were teaching geometry then weren't active in mathematics also, but it wasn't like it was David Hilbert or research mathematicians that were concerning themselves with developing this diagrammatic symbol system. The initial paper that we found by Latham Baker, published in 1902, he was someone that was interested in helping students in school geometry make better sense of the things they were trying to prove with diagrams. And there, it's a very interesting paper to look back to, because he does... And there's some images of it in the paper that we published, but he does lay out these challenges and make specific recommendations for how points should be labeled, how angles should be labeled, how we can vary the weights of our strokes, and that could tell students this is a given quality, whereas this is a quality that you're expected to prove. And it seems like he really did want students to be able to use the diagram to almost as like a self-contained notation system to operate on the geometric concepts that they were dealing with.
So can you tell us a little bit about the books that you then chose to study? Just which ones did you pick, and then what was your process for kind of just going through those, and then I'll ask you about what you saw in there.
For our work, I think this is a challenge for anyone interested in doing historical research with textbooks. There's always this question of just identifying the corpus and finding the books themselves, and we wanted to be deliberate and try to find books that were in circulation, books that were used with specific publishers. One publisher tree that we worked with was Macmillan, which I think became McGraw-Hill. Like, all of these publishing houses over the years have merged, and but they have roots that go back to some of these older mathematic publishing companies. The challenge, though, that we found is that, and this was talking with research librarians at the University of Michigan, and even just through our own work trying to search where stores of these old textbooks might be, is that they're specialty collections that I think Michigan State University has one. We have one at our research library at the GRIP lab at the University of Michigan. The University of Chicago has one. I think the challenge there is that people don't think to save or curate textbooks necessarily the same way that they do other kinds of literature, other kinds of books. And so the reality of what you end up with is what you can find and what is available even though it might have been, I think if we were to build on the study or do a more ambitious study, it would be nice to have more textbooks from across these eras and to try to find out more. Like we did look in I think it's the publishers. There's a publishers annual that like talks about what editions of what books were in circulation during which years, and that was one resource that we could use to just make sure, okay, this textbook is available. Do we actually have reason to believe that it was in circulation or being used at that time? It's like, okay, yes, we do.
Okay. And so then that allowed you to look at thousands of diagrams, speckled across the 20th century, basically. So in the article, you go into a lot of detail about some of the findings you have there. And for this interview, I was just wondering if you could talk about some of the general patterns, if you could kind of boil down the thousands of diagrams that you've analyzed.
I think something that we didn't talk much about the article, because in the article we focus on diagrams about triangles, triangle congruence, or proofs about triangles, and we made that choice deliberately just because there is so much variation among textbooks that triangles were sort of a safe territory as far as 100 years ago. That was still a key part of the geometry curriculum. It's still a key part of the curriculum now, and even if there's differences in how the diagrams are being used, the theorems at stake and the amount of material that got covered was somewhat comparable from then to now. That's what we report a lot about what's different in those diagrams in the paper. But something else that we noticed that we didn't get to write about for this study was just the way that different visual resources varied depending on what the diagram was about. So like one example has to do with probably after 1950, using dots, like a visual dot to represent a point, started to be something that happened more frequently in geometry diagrams. There actually is one book, I think from the 40s, where at least in our sample, that was sort of like the first book that actually was making any kind of use of that dot point convention. So that seems to be something that emerged over time in the early part of the first half of the 20th century. But depending on what a diagram is about, it seems like the diagram might have different visual resources to represent the geometric parts. When you're dealing with diagrams that deal with like points in space or things that are intersecting, open angles, there it did seem like in the newer textbooks, dots on points were used more frequently than in the case of when you're dealing with quadrilaterals or triangles and you're dealing with whole figures. You don't necessarily going to have dots at the vertices of the figure. And again, that's not to say that there's no examples of that in newer textbooks. But from our study and from thinking about what some of the patterns are, that was something that was interesting to us that we'd like to write more about. We just haven't had the chance. And we didn't have the space in the current study to really elaborate on that.
That's an interesting one to think about. I've noticed that for points, because when I'm using Geometry Sketchpad, I always feel like if I have a polygon where there's two line segments meeting, I don't want to also have a point there. For me, for some reason, I just feel like it's tacky to have the point there when it's not really needed. So that's curious to kind of see that happening, points being used in certain cases but not used in other cases. I'm curious if you saw other patterns, looking across, that you want to share as well.
We certainly describe the kind of range of ways that these visual variations could get used and what they mean when they are used. But something else that we noticed is that it's not as if these are rules that people appear to be following, consciously or strictly. And so that would be an area that we are excited to use the kind of framework that we map to go into more detail and to try to find out, does it vary by what the diagram is about, right? Is that sort of like the key? Like maybe diagrams about parallelograms or diagrams about triangles, diagrams about circles have different kinds of conventional ways of using these resources. But from our, we don't have claims like this in the paper for a reason because they're speculative, but it did seem to us that, just getting back to this example of like the dots, it does seem that in some cases, it makes sense where you'd have a dot and you'd want it emphasized, but then in the same textbook, maybe a diagram that appears later on the page or on a different page, you would think that an emphasis, an emphatic dot would appear in this instance too, and it doesn't. And so it isn't necessarily clear to us that this range of choices that we mapped is being used sort of like deliberately or consciously by people that are writing textbooks right now. And if you think about something like GeoGebra, which it's interesting you should bring that up, a lot of what we're talking about right now, about the diagrammatic markings and the use of line thicknesses or even the use of color, these appear under the, if you go to the options, they're called like decorations or like other properties of the figure that's like a congruence marking. I don't really consider that a decoration. Like that's something that can be kind of essential to the diagram, and it conveys key information about what it could be used for. And yet they are these things where in GeoGebra you can turn these on or off at your own discretion. And I think it's a good thing that there is that flexibility. I'm not saying that it shouldn't be like that.
Right.
And this is true of any dynamic geometry program. But it does just seem interesting that this range of available choices and the existence of the available choices doesn't necessarily compel people that are using them to create diagrams to do so systematically. And that's, I think, something where we think this study and helping to call attention to how these different things could be meaningful for different viewers of diagrams could be useful. You could sort of think more carefully about, why am I making this a dotted line as opposed to a colored line, as opposed to a thick line?
Yeah, and to me that gets to like the next step after your study about what is the motivation for those choices. From your perspective, it seems like you think a lot about the students' meaning making and how it might support students' learning of these geometric ideas or allow students to take up the ideas. And that, I would hope, is one motivation for deciding, do I want a dashed line? Do I want to emphasize the point? Do I want to make it thicker? Do I want to mark congruent sides? It's like to have that be a pedagogical choice in some way. But I'm sure it's not always that case, because it could also just be a style choice by the publisher. Like, we think this looks better on the page, so we want to make that choice. Or it could just be kind of this not very thoughtful choice, like, oh, why is that one dashed? Oh, I guess it is dashed. Or why did you do them all the same thickness? Like, that one might be a lot of times like an implicit choice of to not make one thicker, but to just make them all the same thickness. Like, why did you make them all the same thickness? Oh, I didn't even think about it. Like, I never even thought of emphasizing one over the other. And so it's kind of like, could be pedagogical, could be a layout or a print kind of style choice, or it could be kind of this like sort of absence of a choice, so just a default kind of position.
And it does seem, at least in newer textbook, and there's research in the last 20 years that talks about the textbook publishing industry and how it's changed over time, but it certainly does seem to be the case that the visual art that goes into a mathematics book is not even necessarily something that's controlled or authored or edited by the people that are writing the textbook. Like, what I meant, because in most cases those are separate permissions. Like, you don't necessarily get the permission from the textbook, from the textbook author, but you have to find who made the diagram and get permission from that person. And that's not to say that the people that are writing the tasks don't have some placeholder for what the diagram looks like, but it certainly does seem like there would be an opportunity for, I want a diagram of two lines tangent to a circle, to then end up as, well, we have this many parts of it, we can use this many different colors and these different strokes because that's going to look nice.
Yeah. I think, too, and that looking nice gets away from one thing that I connect to your work, which I'm thinking about the mathematical practices, and one that I've been focusing on recently is attending to precision. And to me, these markings have big implications for attending to precision, because you can take a geometric sketch or this geometric diagram that lacks precision, and now you can put these little hashes on it, or you can put this little box on the angle, and now that actually makes it more precise. It's like, okay, now this means a precise thing, that these sides are congruent, or that angle is something specific. So for me, I really am thinking a lot about the layout that you have there, and then thinking about, okay, how does this affect opportunities to engage in attending to precision, or does it give the teachers or the students something to engage in discourse with as they're trying to do attending to precision? Because like you said, it becomes a semiotic kind of resource for meaning making in a broader sense.
Right, and I think it also, along those lines, becomes an opportunity for, like Crescent Van Loen, I apologize if I've pronounced the name incorrectly, but they've done some more just general remarks about it's almost like a modality gulf that exists in the teachers versus learners. Teachers sort of being expected to be able to do things like know when I'm drawing a diagram in the classroom, if I want to circle something or emphasize some part of it, and kind of use this fuller range of available choices to make this text, but then students aren't necessarily being taught or even told that those choices are available or what they mean when they're being used. And so you have this, students are getting these like really rich and visually varied geometric representations to accompany the problems they're doing, but then in most cases students aren't even expected to draw diagrams on their own. Diagrams are provided, and it isn't necessarily clear that thinking of adding a hash mark or thinking of varying some other property of a diagram could be a way of more precisely representing the situation that you're trying to solve.
Yeah, or they're told you need to put arrows on your lines, but it's kind of just told as you need to do this, and it's not really a full conversation about the precision of the diagram or things.
Right, like without the arrows, that might maybe that's a segment versus a line, so the arrows help indicate that it's not something that's limited. It's
right. Yeah, and sometimes it can seem nitpicky where it's like, even if everybody kind of actually knows what is meant by that line, some people can still be nitpicky about, I still want to see the arrows on it. And so then it's kind of like not really about the meaning making because they were all on the same page, but then it's kind of just seems like this, arbitrary technicality of you need to put these arrows on there. It's like, you know what? 100 years ago, the arrows didn't even exist yet. So it's not like it's a mathematical truth that it has to have these arrowheads on it.
Right.
It's a convention, and so I think it's important to walk that line. But if it has use for thinking mathematically, then emphasizing it in that way can be valuable. My guest is Justin Dimmel from the University of Michigan. We're talking about his article in JRME. So, Justin, just a last question on this article. I was wondering what you see as implications for this study, and that could go in a couple different ways. So I'm curious kind of what your thoughts are looking at this one and impacting the field.
For one, I think the implications for researchers, for people that are interested in examining diagrams, I do think we've provided an initial survey of some of the different analytic parameters you might investigate if you were trying to describe these visual differences that are possible among the diagram that's trying to represent roughly the same geometric situation. Mm-hmm. But then I think for geometry teachers or for teacher educators of geometry teachers, I think it helps approach geometry diagrams with fresh eyes. Like I always like to reflect on my own experience learning new mathematical representations, and things like my initial encounters with diagrams from category theory or with diagrams that are used in topology, where there's features of these diagrams that are completely transparent to the mathematical experts that are teaching me, and yet coming into it initially, there is a learning curve there of understanding that yes, we have a blob on the board, and that blob represents some topological space. But even though the blob is smooth, and maybe if you were to treat that as a specific topological space, it might have several nice properties. We kind of understand that, nope, this is just a blob, and we're using the blob because we're not really sure what else to do when we're talking about the realm of things that are possible, and topology is so vast. So I think to me it helps think of that encounter and needing to unpack and understand what the representation affords or doesn't afford. The work that we've done to describe textbooks and to think about how complicated that initial encounter for geometry diagrams in textbooks could be for students helps just think about those representations as worthy of unpacking further and understanding better.
Mm-hmm. Well, thank you so much for that work. I do have one last question for you. So this one, you've just gotten your PhD and you're just setting out to the University of Maine to really keep your career going. So now imagine that wasn't happening. Imagine you weren't in mathematics education at all.
A different life.
Yeah, what would you be doing with that different life?
What would I be doing? It would definitely involve being on the water as much as possible. So maybe it could be something like, maybe I'd be a merchant marine. No, actually I don't want to say that. But I think in all seriousness, if money were no object, if it were just follow your dream and do what you can do at all costs, I might want to be a professional ocean swimmer. Now I don't have I'm never going to give Ryan Lochte or Michael Phelps a run for their money as far as swimming prowess goes, but the thrill of doing a long distance open water swim race is, I'm able to keep doing that as a hobby, but swim coaching and training people swimming is something I really enjoy. And if I weren't happily invested in a career as an educator and researcher, I might be trying to make it as someone that is, if not competing in swimming, at least coaching swimming and getting people excited to be in the ocean.
Right.
In fact, right here at Navy Pier, there's a swim every September called the Big Shoulders Swim, and I've done that a couple years. My wife and I have done it together, and it's really just a wonderful experience swimming downtown, sitting among these skyscrapers and using those to navigate the course. So I might be doing something like that.
Yeah, and moving from the Great Lakes water that you've been around for several years now in Michigan over to Maine, with now you will be actually have some ocean opportunities.
We are moving back to the ocean, which is exciting. Although we do love Lake Michigan, especially that it's unsalted.
Well, thanks so much for taking the time to speak with me.
Great, thank you.
Thank you for listening to this episode of the Math Ed Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.